Yeah, so we are WiNoDa Knowledge Lab for those who just joined us, and this is a webinar series on data science. So this is our speaker, Tim Conrad, and we are doing this in English every second Tuesday from 12 to 13 Berlin time. And we already discussed, so Tim already presented introduction to data science and machine learning. We had a brief introduction and then a hands-on session last week. So this week we are starting with introduction to deep learning. And if you missed previous sessions, you can just find them on YouTube. Yeah, we posted all of them as videos already. Just can just go and watch it and follow step by step. And then when you are so far, you can register for the following sessions. Know that you need to register for each webinar separately. So this is for our new participants. And just a quick promotion, we are also planning a workshop, Decoding Berlin, Data-Driven Insights into Museum Objects. You can see it here. And I'll send the link to the chat. And the idea is that it's first it's limited just for 20 participants. And the idea is that we'll show you the Museum for Natural Sciences behind the scenes, and then you'll have an opportunity to look at the data sets coming from museum collections and develop your interdisciplinary ideas with researchers from other fields. So if you are interested, just check it out on our website, and I'll paste all the links to the chat. That's it from my side. And now, Tim, you can start.
Jo, gut. Okay, then welcome to the fourth session of our webinar. Today, as you can see, is a session about deep learning. It's a gentle, I would say, introduction to deep learning, so we will not go too much into formulas, although there will be one, I think, that explains you some basic idea about the atomic parts of a neural network, which is mainly the basis for deep learning. But I will mainly try to give you the ideas of what you can do with deep learning and some of the overarching concepts, if you will. Okay. Yeah, we saw already. This is the fourth part of a series. And yeah, without having listened to the previous ones, you will be happily following today, I hope as well. However, there will be one or two references to at least the last two sessions, because we will compare a little bit what deep learning, how deep learning compares to machine learning. And there will be one or two things, backlinks, but as heard, you can also go to the YouTube channel and then later on listen to the previous sessions and then see how the connections actually work. Deep learning. If you put the keyword into your favorite search engine, you will get, I don't know how many millions of hits, many pages and documents and videos and images that try to explain you what deep learning really is. You can go also to Wikipedia and other encyclopedias or any overview articles. And at the end of the day, you will probably just overwhelmed by how many different definitions at the end there are. I picked these three, mainly I think from the Wikipedia article, because I think they actually describe what deep learning really is quite nicely. First of all, it says, well, it's a branch of machine learning. So it's somehow connected to machine learning. So what we also looked at in the last two sessions. We will also look in a second about what that really means. Then the second thing is actually, I think, the most important and interesting one, because yeah, it has been characterized as a buzzword kind of, or a buzz phrase maybe. Deep learning is more like a kind of a maybe not even really a concept, like some buzz phrase that says, oh, we do now everything with deep learning. There you go. And no one really understands what it means. And everyone understands, wow, it seems to be cool and it seems to be hip and state of the art and so forth. But at the end of the day, it is a rebranding of an idea that is around since the 40s of the last centuries, 40s and 60s and 80s. There have been done a couple of large milestones. We will not go through them today, but yeah, you can look at any history of technology if you want to read about it. And at the end, this, what we see today is really just a super fast version or a super large version of what has been described in the 60s and 80s of the, as I said, last century. So it's really nothing new. What is new, and we will also see about that in a couple of slides, is that it's just getting larger and more powerful. But the main idea, the mathematics and everything behind it is super old. And the third thing is, it is often presented, and that's important, as a step towards realizing strong or generalized or AIG AI, which at the end means something like you will have a system, some strong generalized AI that is acting like a human or even better because that system has more knowledge, not knowledge in terms of it has read everything. It can draw conclusions from the knowledge it has seen or read or wherever it got the information from. Whether or not this will be at some point in time realized or achieved, unclear. There are many different opinions from scientists. There was, I think, recently an article by Sam Altman from OpenAI who said, well, probably we will hit this generalized AI in 1 or 2 years latest. Other people say this will never happen. Yeah, time will tell, and we see what will be happening. At the bottom here is just a chart from Google Trends that is supposed to show you a little bit when the more or less general interest in deep learning began. Now really based on one easy metric, which is how often was the phrase searched in Google in this case. So we talk about the phrase deep learning, and you see that there was something. So it starts here in 2004, something until maybe 2012 or so. Then it slowly got more, and then it actually spiked once or twice here and here. Although they changed these little lines here to say that they changed a little bit the way they counted the views or the search terms. So I'm not really sure was this really that much spike. But you can see that over time it actually became much more interesting to people to at least read something about it. Might or might not be important, but the point is that before, say, 2010 or so, deep learning was really not on everybody's radar. And today, everybody's talking about it and everybody's interested in it. What can deep learning do? I guess most of you have an idea what they think that deep learning can do, or maybe even try it on a day-to-day basis somehow. I collected some examples that we can look at now together, and maybe you find it interesting and use it also later on for your professional or private life. But of course, it's just a couple of examples, and this technology that is behind this deep learning is more or less general. You can do, if not everything, then almost everything when it comes to problem solving or data analysis or data generation with the technology. Now, deep learning is about using networks. We said that in the beginning. I will also later on explain you really what a neural network is, at least the basics and how it works. And this neural network, which is the actual underlying technology of deep learning, it has to be, or has become one of the major areas in which stuff is happening. So over the last couple of years in this neural network area, a lot of research and money has gone into. From a research perspective, a lot of method development has been taking place, a lot of method improvement has been taking place, how neural networks can be analyzed, how they can be used, how they can be trained, also a term that we will explain a little later. But at the end, how it can be really brought forward to help in data analysis. And also, as we will see in a minute, not only analysis, but also in terms of data generation, which is something that neural networks haven't really been built for. But today time has shown, think of ChatGPT, that actually generating things, texts and images and so forth is also a really big domain of these neural networks today. And what's interesting, that's also over the last couple of years, that in many problem areas, I will show you 1 or 2 examples in a minute, neural networks have actually established the current state of the art. So when you think about image analysis or speech recognition or today text generation also, most of the leading algorithms are today neural networks. And in many cases, they actually exceeded the previous benchmark. So how good a particular problem was solved by another technology before, by large, by far. There's this one example where there was these really big competitions or scientific competitions when you give an algorithm an image and ask the algorithm, okay, what do you see in this image? And then the algorithm says something like, oh, I see a forest, or I see a animal, or I don't know what. And in around 2010 or so, the first time neural networks have been introduced to these problems. And before it was more or less possible to find 5, 6, 7, 8 items on these images. And neural networks more or less were able to actually describe the whole image, including which type of trees there are, including which animals are hiding, which not even humans have sometimes seen, and so forth. So it was just a enormous push in what this technology could actually achieve in very, and this is now also the point, in very narrow and specific domains, in this case, for example, image analysis, but nevertheless, many, many more of these areas have been evolved since then. Some of the ideas are, or of these areas are, for example, translation. Google is using this technology since a quite long time. So this is an article from 2016, actually, where they describe how neural networks made their translation capabilities in their own, well, inside, I think, the Google search, and you can use it, but also externally, so translate of Google, so you can find it. And since a long time, machine learning, and this is mainly neural networks, though, have been pushed how far languages can be translated and what quality language can be translated from one to another, just using this new technology. This is what I said earlier, an example for image segmentation, image recognition. So this is also actually quite an old example, nevertheless gives you the good idea about what's happening there. So you present the algorithm image, in this case is the scene here of some touristic area, and then you ask the algorithm, what do you see there? And it describes thousands of items that it would be possible to, here, just as some of them are depicted. So it finds building, it finds humans that have a bag, and it finds a bag, it finds bicycles, and so on and so forth. And if you make the algorithm to actually go deeper, it'll find shoes and whatnot and stains on the floor. So it can really this word is quite strong, but superhuman level, it is really able to understand this image, understand in terms of finding concepts that it has seen before. And it does that in an incredible speed and an incredible detailed. So that's why I meant earlier, in these competitions, neural networks are the clear winner, and in most of the cases, much more detailedly than actually humans are. Image caption generation is something also very interesting, maybe a little bit more from the academic point, but it goes together with the previous image. So once the algorithm can find things that are inside the image, it can also actually try to make sense out of it. So here it says there's a man in a black shirt is playing a guitar. So the algorithm found that there's a person wearing a black shirt and there's a guitar and so forth. And out of this information, it now generates these captions. The other ones you can read yourself. And this is also something where these algorithms become better and better, literally by the day, where they understand in terms of which concepts, which items are inside the image. And then out of this information, they go to the next level and generate, say, captions, or generate, if you want these days, even a text about it, what's seen there, and give you back information and so on and so forth. So it's really incredible combining then these things from understanding concepts to generating to some text to put the concepts together as is possible these days. Speaking about generation, this is maybe something that many of you have played with already. So image generation from text became, over the last maybe 2 years, incredible. What you can do, the quality of the generated images is oftentimes not really, you cannot really understand whether or not this image has really been taken from a professional photographer or whether it was generated. Clearly, the guy on a horse in the space is probably not taken by a photographer. However, the quality with this image is created in the details and the lack of obvious problems in the image, except of the idea that this will probably not happen, is just incredible. So if you use one of these services these days, you can generate pictures that are in many cases not really identifiable as not being generated by a human person, in this case, maybe with a camera or so. This is also another thing that is really interesting these days, image generation from concepts. So this web page, it's called thispersondoesnotexist.com. If you open that web page, you will find that some person is looking at you. And if you reload the page, that's another person, looks totally different. And the point behind is that these persons have never existed, as in they're all generated. And if you look at these pictures from these people, you will probably not see that they're generated or computer generated. You might think, well, sure, this is from party, some photographer taken or some image taken, and now they just put the website. But no, the image or the neural network underlying this technology, this web page, has to learn what a face is and what a background is and what pieces of the faces are and what are the ratios of the nose to the ears and so on and so forth, and what is reflection and so forth. So every single image here is generated artificially with the concepts learned from data it has presented with. So for example, a large database of images, of face images in this case, it extracted the concepts and now can use this concept and generate as many images if you wish. There's also some kind of control if you want. So there's even networks that are controlling these neural images in terms of poses or types of the faces. You can tell it, give me a face that looks from left to right or from right to right, or that is even upside down or whatnot. And then these concepts are just put into a particular site or direction or so, but the concept face is still the one that generates all the time. And then my last example is playing games. You probably also heard about that. It's also quite old these days. So I think 16, 17, and then later on in I think 18, a company mainly owned by Google also, or part of Google even. They created algorithms that could play, or started with chess, and they went on to shogi, which is some, I think, Japanese version of chess, and then went on to Go at the end. And they were able to actually show or build algorithms, again, learning algorithms that were built on neural networks or deep learning technology that were able to beat, back then the current world champions in this games, with a speed and a accuracy that has never been thought before that is possible, because these games are so complex that one assumed that only a human mind and this way, or a human brain could master these games. But yeah, well, obviously, with these deep learning approaches or technologies based on neural network concepts, they have been found algorithms that can do this now. Good. So this was the idea. Okay, what can this technology do? Why can we use it for? What can we use it for? Data analysis was a little bit the theme around it. At the end of the day, playing a game is data analysis. So I see a current status of maybe the board game in front of me. Maybe I know already how games can be played. I know the rules. I know maybe historic games that have been played. And from this analysis of the data that I have, I can then move forward and say, okay, given this current situation, these are the next couple of steps I have to do to win, maybe even, or to just make a good game. And therefore, also playing a game can be written down in language of data analysis if you want. Okay, but let's have a look maybe also from the last two sessions, what we already learned about machine learning and how this relates to deep learning. So at the end of the day, this is more or less what people think these areas are and how they are connected. So the broadest area you can think of is more or less what people call artificial intelligence. So everything in which machines are supposed to mimic human behavior. So algorithms that allow machines to mimic human behavior is usually called artificial intelligence. So that's the largest block you can have. And then part of artificial intelligence is machine learning. That is more or less a subset of artificial intelligence, where it is mainly based on statistics or statistical methods, at least, to enable machines or the algorithms to learn from data. So the more data, the more experience they see, the better they should be. But at the end of the day, it's again about learning or being able to predict something or to recognize patterns in data and doing data analysis at the end. And then a subset of machine learning is then deep learning. And deep learning, again, is just just a rephrasing of the good old neural networks idea that has been around since many years. So the idea is that it's a subset of machine learning, which makes the computation of these neural networks, or in this case, multi-layered neural networks, and again, we'll talk about in a minute what this really is, feasible. So it uses neural networks to do data analysis at the end, similar to what machine learning algorithms do, that are more on the classical side, so statistically based. So that's the same, but use a different technology, neural networks in this case. But at the end of the day, deep learning is just another machine learning algorithm that is just now specifically using neural networks for it. Good. And then to connect it back maybe a little bit to the last section, to sessions, machine learning is here on the upper part. So think of machine learning, you input as an image, so an image of a car in this case, and the output that you would like is that your algorithm tells you whether it's a car or it's not a car, right? You show an image of a car, and then the algorithm should decide what it is, and that gives you some answer. In the machine learning case, I have an example in the next couple of slides, and also what we did last time, to solve this task in the more classical statistical oriented way. So you first should select an algorithm or a model that you would like to use. Then you should maybe understand which features of the image you need to use and to use it with your models. Then you need to try out a couple of models, which one actually works best. Once you have decided on that, you can do or perform this classification task, given the model you selected, given the algorithm you selected, and given the features you selected. So features could be, I use the pixels of this car, or I just use the surrounding line, or whatever you want. But you have to specify all that. And once you have it done, then you can use this whole set that you put together and classify something with it, and you get hopefully the right output. Deep learning gives you the same result at the end, and it uses the same input, but it does not need this selection of model, algorithm, features kind of stuff, because it's always the same. Sure, in the deep learning world, you might need to specify whether you have here, this is 1, 2, 3, 4, 5, 6, 7 so-called layers, or 6 layers, or 2,000 layers. And you might want to specify how many of these circles you have here. We will also come in a second to what it really means. So the size maybe of network, or the particular architecture also. There are different styles of networks. By the end of the day, you decide, I want to use the network, and that's it. And then the neural network is trained based on data. We will also come to that point, and it can then do what you want it to do. So all these selection of models, algorithms is just not happening. You say, I need a neural network, take a neural network, you train it, and then you can use it to classify your input. Again, same thing, you take it to classify your car, pixels maybe as the input, the thing runs and does its magic, and then it spits out, okay, this is a car, or this is not a car. So deep learning is the same thing as before in machine learning, from the input to the output side, but what's happening in the middle, that's basically what changes. So you're not, it's not needed that you deal with all different possibilities. You just say, that's my technology, use it, train it with the data I have, and then it spits out the results you want. Good. So just to focus a little bit on this last point. So what we did 2 sessions ago, we had this problem where we were interested in finding a function or a mapping between Celsius and Fahrenheit. And what we did is that we collected data. These were our blue points here. And then we were looking for a model that would reflect our data that we collected. And in visual terms, it was, we have our blue dots here, and we were looking for a straight line that is representing these blue dots as good as possible, as in most of the blue dots should be close to this red line, right? So of course you can also draw different lines, but this is the best one in terms of it's closest to all these blue dots. So that works, that's nice, that's fine. But what we needed to do before is that we needed to specify this model. We needed to say, okay, look, we are looking for a straight line that matches this point cloud, this blue point cloud. This was our choice of a model. So yes, it worked, but we had to do that. If we had used another model, it might not have worked. In this case here, we have another data set now. So we have this blue data set here. If we would use a straight line, so a linear model to match this data set, it doesn't really work. I mean, sure, it's not super wrong, but at the end, it doesn't get all these bumps here. So this is not a good model. if you take some sinus wave or maybe whatever trigonometry function here, then it matches much better, right? So now your model is, this red thing here, and it matches now your blue dots much better. So you went from a straight line linear model to something else, or you can even go even further and have a super complicated model here in red that you can also make to fit your data. But here then something happens where it fits all your blue points, more or less at least, but it then some crazy stuff at the end. So the main problem with machine learning is, once again, the classical statistical ones, it works, but you have to find good models. You have to specify them in front, and then you have to fit your model to the data. Choosing the right model is the key. And in neural networks language again, you don't find the real model. You don't specify the real model. So you just specify you want to use a neural network. You again leave it run and leave it to the training magic there. And at the end, it spits out this green model here. That's what's generated by the neural network now. It has seen the points before. It started with something crazy, and then over the training process, it converged, as we call it, to something that works well. And it says, well, this green thing is a model that I found for you. Now you can use it and do whatever you want with it. So the point is from choosing a model, these red things here, or red models here that you have to specify machine learning case, to dear neural network, find the right model for me and tell me how good it is at the end, and then I can use it for whatever I'm interested in doing with it. So that's really the jump from the machine learning part to the network part. Another example, just for illustration again, if you think of this and you are asking for a good model that can separate the two colors, red and green. And we start again with our most simple model, which is a linear model, which is a straight line. Yeah, wherever you will put the straight line, you will not really separate the colors nicely, right? So you can put it wherever you want. It will always be a mess in some way. But if you ask a neural network to find some kind of model to separate this, it'll come up with this. It will find this model that is now illustrated by this blue line here, and it will say, well, there you go. This is your model. If you want to separate these two groups, red and green points there, this is the model you can use. Whether this model is then robust against noise and so on and so forth is a very different story. But the point is that these neural networks are so powerful, and if you give them enough parameters, they can fit whatever you want. So no matter how weird your green and red points would be, it'll always find some kind of separation line in between to actually be able to separate that. And this can be used for classification tasks and whatnot. If you're interested to play with something like that, I'll post you the link to the chat here. This is a really nice site on which you can play and also see the power of neural networks. Without having too much understanding of the internal mechanics, but just to see what one can do with networks and also what these different architectures a little bit are. So if you are bored at some point, check it out. Okay, good. But we were talking now, I was talking a little bit now about data and training and so on and so forth. And that's to say, I think the main point when one talks about neural networks and deep learning in particular. So when does one use deep learning? What you see here in this little chart is amount of data. So how much data do you have on this axis here? And performance, or how good a particular technique, if you want, is performing. So how well is in accuracy or whatever you're interested in. And if you look or just concentrate at this part here, then you see you have not much data, so little amount of data if you want. And if you then follow this curve here, which is the traditional machine learning, so the more classical statistic-oriented ones, you will find that if there's not too much data, these models perform actually quite well. But at some point in time, the more data you get, they don't really improve anymore. So at some point in time, that's it. That's the best they can do. And if you now, on the other hand, follow this curve here, which is for deep learning neural networks or deep neural networks, you will find that in the beginning, if there's not much data, they actually don't perform very well. And only after a particular point in time, they become better than traditional machine learning, statistical machine learning models. And then they become much better. Also, sure, at some point they saturate, either because the problem is not really solvable and 100% accuracy doesn't exist, or when they really achieved 100% accuracy, they were always right in some way. Between there's then shallow and medium neural networks. We'll not talk about that today. That's more or less the complexity level. So shallow is not really complex. Medium is medium complexity, and the deep is the super complex ones. So the point is, the more complex the neural network becomes, or the architecture you choose, the more data you need. And when we talk about more data, we're not talking about 10 or 20 or 50 examples that you need to use and to train it with, but we talk about hundreds, thousands, or millions or billions of examples. So if you have some collection of items and you want your network or your algorithm to learn these items, whether it's a pot or a window, or this idea of I want to recognize parts or items in image, we're really talking about hundreds of thousands or millions of images you need to actually train the network with. If you don't have this many items, deep neural networks are not the right choice. Then you really go back to the traditional statistical machine learning, as we covered in the last two sessions. So this is really this data aspect. So machine learning from a classical perspective makes a lot of sense if you don't have too much data, talking about hundreds or thousands maybe of samples. If you have 100,000 and millions of samples, then neural networks or deep learning technologies are probably a better idea because they are just more powerful when it comes to these large data sets. Good. One explanation also of this jump here, bidding of 10,000, 2010, is that GPUs, so graphic cards basically that were back then used mainly for gaming and on large gaming computers became actually quite cheap. And people understood that these GPUs are quite powerful, well, subcomputers, if you want, inside another computer that can be used to train and use deep networks or neural networks overall. And when they became so cheap that more or less everybody could afford one, people really started playing around with it, also in the research and scientific community, and improved algorithms, made them better, made them faster. And at some point in time, there was just this point reached where someone came up with this very, very efficient implementation on how to train neural networks. And from that day onwards, basically, it became able to train and use really complex deep neural networks. And that was the point in time where people understood that they can just now throw these new algorithms on problems that were not really solvable before or not very well solvable before. Because also, that was the second part, or third part maybe, large training data became available. So it was this era of big data that really took off, where people really now could afford also large storage devices, and it became cheap to actually have them in your own science institute, if you wish. And these three things came together. So cheaper GPU, graphic cards, the algorithmic advancement that were done, and the availability of this large training data. These three things came together, and then was basically the time where people just threw it on everything, and everybody was just super, let's call it happy that it works so well. And from that time on, really, this technology became hyped, and again, to the point of today, where we have AI or AI, deep learning-based AI, in so many parts of our lives that most of that we don't even recognize anymore. Let's leave it there. Okay, so that is the important part. So deep learning on networks is great. It's accelerating. It's solving problems that we couldn't solve before, but only, and that is a really big but, if we have a lot of data available. If not, go back to traditional statistical-based classical machine learning, and that will do a better job. Okay, so in essence, deep learning can more or less do everything that machine learning does, but not the other way around. Machine learning is useful and also in most cases better suited when the data set is small and well curated. So you have data, you have it pre-processed, it's curated by you or by your team or because someone else has done it. Then really machine learning is better for you. And deep learning becomes powerful and even extremely powerful when the data set is large. Hundreds of thousands of images, hundreds of thousands of pages of text and so forth. Then is the point where deep learning becomes more or less better or even much better than what we would solve with traditional or classical machine learning algorithms. So limitations. Deep learning is computational expensive. So when we talk about companies like OpenAI, for example, and they're running this ChatGPT and these services, we are talking about €1 million of electricity costs per day. So training, maintaining, using machine learning based on these graphic cards, they are very, very expensive in terms of energy. If you have a current state-of-the-art graphics card in your computer, you need a power supply that is 4 times larger than you would usually have. So just using machine learning based on GPUs, in this case, on neural networks, deep learning, is expensive. Not only computationally, as in it might take some time, but also from the energetic perspective. And then, yeah, well, the other point is then the time perspective. So training a large deep learning network is easily taken weeks and months and years if you don't have enough resources. So if you have only one graphics card and we're talking about millions of images, this can take a while. And again, a while not being a couple of hours, but being a couple of months. So you will not do this. So what you will do is you will again go to some kind of compute cluster if you want. We have at Zusatz, for example, we have a large GPU clusters. Many universities have that these days. But that's where you will do the training. Once you have done the training, however, it is super cheap and computational, from an electricity point as well, to use it. So once you have a neural network, it is considerably cheaper than what the training would have done, but also using it is actually not the problematic anymore. So if you train the network for months and years, maybe potentially, using it can be done in a couple of seconds. So once you have that thing trained, you can ask a question and the answer to the question comes back in a couple of seconds. So for example, there are these large language models these days, ChatGPT and others, that have been trained on thousands of GPUs for many, many months. So normal people can obviously not really afford it. So think of maybe €1 million that have been done or spent on just electricity to train these things. But now you can download this. It's many of these language models are downloadable for free these days. And you can use it. And on your normal laptop, maybe it has a GPU, not a really big one, but a normal one, you can use this super large model. It might take some minutes to generate an answer, but it's usable. So this really big thing that has been trained for months and months and months, you can now use to answer a question, well, depending on the size, within seconds or maybe for the larger ones, even minutes, but it works. So that's the big difference, right? Training, super expensive, super computationally extensive, but using deep learning networks or neural networks, deep neural networks, is then kind of cheap again in comparison. Okay. Good. Now I talked a lot about these networks and I tried to give you a flavor and overview of what this really is and what it does. And now a little bit towards details, what is underlying. So if you now fall asleep or not interested anymore, I hope you got the main idea between what is the deep learning network compared to a machine network, what are the benefits of it, what are limitations, but again, always the point in the back of your head, oh, if I want to use this thing, I need a lot of data. And next part is now giving you a little bit of the underlying technology or concepts. And then we wrap up at the end, and that's it for today. Okay. Now, a super oversimplified neural network could look like this. The thing in the gray box here, which is called a multi-layer perceptrons neural network. Again, the idea we had from before. So you give it some input. Here's the input of a cat. You run it through the network and you ask it to classify this thing for you and it says cat. So that's what the neural network does, right? Has been trained before, so it knows what cats and dogs are, for example, or maybe only what cats are, and they can just say cat or something else. That's a neural network. Okay. Now, what it does, or what it is in simpler terms, is it is an interconnected groups of nodes. So nodes are now these circles here. And the underlying idea that people had in the 40s of last centuries, and then also a little later again, is, well, let's try to mimic the network of a brain. So in our brain, we have also neurons, which you can also imagine as little circles. These neurons are connected. There are many of these neurons in our brain, many connections of it. But at the end of the day, it is a similar thing. Okay. So in our artificial neural network, we're trying to get the same idea. So we have these circles, we connect them by arrows, which means an output from a neuron goes to the input to another neuron, and then there's another output from here and goes again to a neuron, another input of another neuron. And this is the idea of yeah, at the end of the day, how a brain works. There's much more to it and much more complicated, but super broken down, that's really how it is. Neurons, one neuron does something, gives its output to the next neuron as an input, and then this neuron does something to it. And then at the end of the day, there's something, some result. Again, here from a perspective of image classification, it's a cat. Okay. Now, to make a neural network that we had earlier a little bit, to do what you actually want, you need to teach it what you want using examples. So that's what's called the training. So the basic idea here is I can use this general structure of an artificial neural network, and I can use the exact same structure to recognize images from cats or whatever else, to recognize speech. I say something and it says, oh, the user said yes, to recognize videos, to do data analysis tasks, to cluster something, to do regression, whatever you want. It will be the same structure of an artificial neural network. There might be better structures that are better suited to your task, but at the end of the day, you can always use this basic structure of a neural network. In this case, multi-layer perceptron. Again, your network structure that you need might be a little bit more complicated, might be more of these circles, and that's when it becomes deep or deeper or more complicated, but the idea is always the same. I have a structure, I have examples of the data that I want to analyze. Again, here it's classification, and then I train my network, and then it can do this task I trained it for. Nothing else though. If you train network for image recognition, it cannot recognize speech, and the other way around. So what people do today, if you have multimodal ones, is they stack together different neural networks, and then the network decides, is it speech? Oh, then I use this submodule. Is it an image? I use this submodule. Is it a video? I use this submodule, and then they can put stuff together at the end. But one neural network, at least today, can only perform one particular task. And then again, going for a simpler version of this to a deep version is just that. You just make it more complex in a way. In this case, we added more layers now, as it's called. So here's my input. So it could be again the cat, and then it's a cat. It just has more layers now, and that's when it becomes deep. So there's not really a number when a neural network is deep, but think of 50 or 100 or 10,000 or even a million of these layers, one after another. That's what we usually call a deep architecture. But at the end, it's the same thing. This is a simple one here. What people were studying again 60, 80 years ago. And this is then what we do today. It just became deeper as in more layers or more complex, but the usual ideas are staying the same. The basic ideas are staying the same. Sure, today we have also better algorithms, and there's a little difference in the structure and the architectures we're using. But at the end of the day, this is the basic idea. Okay. Now, in either basic or simple, the atomic structure or the most basic building block of all these things are these little circles here, as we saw. And this is what is called a perceptron. Perceptron uses, or is looking more or less like this. It has some input, it does something with it, and it does give out an output or spits out something. Okay. Input we saw before could be the full cat image here, or if you think of a cat image being something with many pixels, then maybe every pixel, every position on the image is the input here that goes into a particular neuron. So you have some input. In this neuron, some mathematics is done. Well, obviously your brain doesn't do mathematics, but what's happening there and on abstract level is actually some computation. So every neuron can do some computation. And then based on this computation, some output is generated. If you really put in some numbers, then what happens is, usually, at least in a computer, we work with numbers. So that's why we're having this numbers idea. What your brain really does at the end, well, you can think of electric current. And then you can also translate that to some numbers or the strength of the current or so. Then at the end, you could also say, well, there's some number calculation going on. Doesn't matter. For now, please bear with me the example that we created here. So there's some numbers as an input, some math is happening, and there's some output. And what's happening here from the math perspective is that every of these input pieces that goes into a neuron has a particular weight. It can be, we see in a second, a 7 or a 5 or a 3. So how much this thing is multiplied with. Then this input multiplied by its weight, so these 3 times this example, is just summed up. So this times this, plus this times this, plus this times this. It's summing here. And then there's something called an activation function that is actually more or less happening in the inside of it. This activation function is doing the following. If so let's say in this example, we have this minus 0.06 times 2.7 and so on. So if you do the calculation as I just explained, you get 21.34 as a result, right? So what's actually here as an input is the sum of these 3 multiplications here. So in this case, 21. Now, what this activation function does is it takes this value and converts it to a value between 0 and 1. So if you want, 0 is not activated and 1 is activated, hence the name activation function. And what you can see here is if the sum of the inputs is, say, below -6 or so, then you will get a 0 as an output. And only if it becomes, in this particular example here, larger than -4 or so, it actually starts to increase. So this is here the value range that this activation function can take from 0 to 1. And around 0, so if the sum is at least 0, then the activation value, so the output, is becoming greater than 0.5. And then at some point, whatever you do, it doesn't become larger because 1 is the upper limit. So in our case, for example, since it's 21, that would be somewhere around here, then the value that we get is close to 1. So as an example, 0.95. That's it. That's what the neuron or this perceptron, the mathematical model of a neuron does. It takes inputs, multiplies it with some weights, sums it up, and then puts it into the activation function here, and then determines the actual output, which will, in this example, be between 0 and 1. Now, the only important thing now that will come in the next couple of slides is during this training, when I present my neural network, my examples, how can I determine these weights here such that the output is what I want? At the moment, it doesn't make any sense whether these numbers or this 0.95 here, that doesn't make any sense to anything. But this will be the strategy from now. So we will find, because the input I cannot control, right? The input is the image or whatever I have a task with, could be the cat image. The activation function is also built into the neural network more or less, so I can control the weights. So this is what training or teaching the neural network something to do will be about. Train the weights and see that we get the right output here. Right output could be the label cat or whatever you're interested in. Okay, so what does the training do? I came up with a stupid, but I find it super funny example where I would like a neural network to understand my planting problem, which is I have some soil in my pot for my plant, and I do something with it. I put in some herbs or water or whatever else, and at some point in time, a plant grows, and sometimes it doesn't. And I couldn't really figure out why that is, but I want my neural network to understand it. And what I did is that I have bought 3 different sensors that measure 3 different things. The sensors spit out numbers, and I can see from how the plant is doing basically over the period of a day whether the soil quality is now good or bad. Okay. So this sensor spits out the number 1.4 here. This sensor spits out the number 2.7, and this sensor spits out the number 1.9. And then I know, because I see that from my plant, oh, cool. With these 3 values here, actually, it was a good day for the plant. Soil quality was good. Or, wow, the plant really didn't like it. So I know it was a bad day for the plant. So I have a class, right? This thing here is a 1 or a 0. Okay. And then I collected some data over the last couple of weeks. I can also make it daily, whatever you want. So I always wrote down the numbers on my sensors here, and I wrote down the plant was not happy for the first 2 weeks, and then week 3, I changed something, and my sensors showed these values, and my plant was happy. And then again, I changed something, and the sensors showed this, and my plant was unhappy again. So just data, right? I collected it. I have some numbers now every week, and I know which class it is, a happy plant or a not so happy plant. Okay, and now I wanted to teach my network to learn given data to then tell me, okay, if you have this sensor data, your plant will be happy. If you have this sensor data, your plant will not be happy. That's what my trained neural network will be able to do at the end. How do I do that? So here's my data set again. So my 3 sensors, numbers, and then the class I know. And what we do is the following. We start a training of the network with random weights. Remember, the weights are the only things that we can control. Input is fixed. It comes from my training data. Output is fixed. That comes from observational data, or also training data from my observations I have. So we can only change the weights. In this, just to make it a little bit simpler, every arrow actually has a weight here. I just draw some now so that it doesn't get too messy, the image, but bear in mind, every single arrow now has a weight. We start the whole process in giving it random weights. So there's just some number on each of these arrows. Now I present a first training data to my network. So I have the 3 fields in my sensor, outputs 1.4, 2.7, 1.9. I tell it to my network. And now comes the part that we discussed briefly earlier. Now I do the calculations that we discussed, right? So remember, the calculation is I have some input, I have some weights, I sum them up, this times this, plus this times this, plus this times this. This gives me some sum here. I put it to my activation function, or through my activation function. I get a value between 0 and 1 out of it. And then this is then passed to the next node, and then the same game goes again. So I do this, I do all these calculations, and then I end up with 0.8 and the 600. Now 0.8 is not what I wanted because I wanted a 0 here, right? Because I know for this measured data here, it should be a 0. The class was 0. So I made an error. The error is 0.8. And now what I do is as simple as ineffective at the end. I will correct for this error. I will change the weights that I had from the previous step, so the random ones in this case. I will change them such that my results gets a little bit closer to what I wanted. I can do this because from the mathematical analysis, I know more or less which of these weights were the most wrong. So I correct them a little bit into the direction such that my result becomes a bit better. So I do that. I go to the next training pattern. I, again, have my weights. Now they're changed a little bit. So they went from 2.4 and 0.1 to maybe 1.9 and 0.2 or so. So a little bit changed. And I present again. I put my data now from this one here, 6.4, 2.8, and 1.0. I have all my weights. I do the calculations. I end up at 0.9. That's quite good. Actually, I was supposed to have a 1 here, so my error is a bit smaller. So again, I change my weights. And again, I change my weights. And I present the next one. And I change my weights. And so on and so forth. And this I'll do now millions of times. So obviously I need, again, to have a lot of data for this. And I will do it all the time. In this really small networks, in small examples, this actually is quite fast. It can be done in seconds. And at the end of the day, I will have a network here that has the right weights to represent my data. And what I can then do with it is I can give it then previous unknown data, so something that I measure maybe tomorrow, and I can ask the network, hey, is my plant happy with that or not? And if the network says, no, your plant is not happy with that, then well, maybe I can already change a little bit of my of whatever I put to my soil to try to make it a bit more happy. Measure again, ask my network again, will it now be happy? So it learns to map the sensor data to whether or not my plant will be happy or not. And it does that through this training process, which is the most stupid you can imagine. You have data, you have outputs, you send your data through the network, see the output, check the output, whether it matches what you were supposed to get as an output. If there's an error, you correct the weights a little bit to the direction that supposedly become a little bit better. You train it again and again and again until it reaches more or less a stage in which it can more or less represent actual data. That's what training of neural networks is. And that brings us to the last slide, because this is how we train this whole thing. Depending on the complexity of the neural network, it can be a very simple network or a very complicated, deep one. But at the end, you can then train it on whatever you want. On animal pictures, I'll put a dog here for a change. On speech, on, again, videos, whatever you want. Playing games, generating images at the end of the day, finding objects in complex scenes, whatever you want. You just need the neural network, maybe a little bit different architecture, so it looks a little different, but at the end of the day, it's the same idea. You need to train it, hopefully efficiently, because otherwise it will really take months and years to train it. And that's the main point, you need training data, as we saw. You need hundreds, thousands, or millions, or even more of potential training data. Neural networks, though, maybe it's the last remark, also work with less training data. And in some examples, there's also good areas or areas in which the neural network is better than a classical machine learning algorithm, even though there's not too much data available. But in most cases, if there's not too much data available, stick to the classical machine learning, so statistical based ones. In most cases, you will get better results with that. Good. And with that, I'll leave you with these ideas. I hope you got the main points of the day. We have some minutes left for questions. And as always, you can put them in the chat or also write me emails later if you're interested. Thank you.